Yeah. I already made those. Yeah. I designed. Yeah. Well, for like it was not long enough.
Okay. I hope that everybody had a really good break. I hope that you also remember that we strangely have a test a week from today, but that's okay. It's we'll have lots of opportunities between now and then to review, not the least of which will be pretty much all day, and the whole lecture or whatever, on Thursday. On Thursday, when we meet, we only cover a tiny bit of new material, and then we kind of put this all together. It's the big picture lecture, if you look at the syllabus, where we kind of, at this point in the class, kind of take a little break and look back and put all this together and realize, hey, this business of general circulation and fronts and air masses and cyclones and anticyclones, it's all really pretty much the same thing. It's just different ways of looking at the same thing. So it usually takes a whole lecture of just sort of reviewing about that kind of stuff to kind of make everybody on the same page about where we are. So today we're going to be talking about the life cycle of a mid-latitude cyclone and cyclogenesis. Now maybe it's just the way my brain works, but to me, to my mind, this is the hardest material in the course. I think today's is the hardest lecture that we do. All right, maybe it's just because of, whatever, I don't know. I think from here on out it gets better. Okay, which I think is a good thing about the course. I like the fact that we get to the hardest stuff early, and that way when other courses are going crazy, difficult towards the end of the semester, we're actually, doing lightning and El Nino and stuff that's actually quite a bit easier to understand than the cyclogenesis stuff. So anyway, I will leave it to you, maybe to you. This isn't the hardest material that we're going to see, I don't know. But to my mind it is. It's unfortunate that this semester, just based on the start date and when spring break fell, that the hardest material happened to happen the week after when everybody's just getting back from spring break and trying to cope. Okay? But at least it didn't happen this semester, say, during midterm week, which is always a bad situation too. Anyway, so the first thing we're going to talk about today is the life cycle of a mid-latitude cyclone. Now, when last we met, oh my goodness, so long ago, we were talking a great deal about this word cyclone, where we talked about this idea that cyclones are areas of low pressure, and they have rotation. The winds around a cyclone rotate counterclockwise in the northern hemisphere. So here's your area of low pressure, and winds around a cyclone rotate counterclockwise. If we're talking at the surface, the winds rotate counterclockwise and sort of spiral in towards the center of the mid-latitude cyclone. You might remember that we called the wind balance, the force balance rather, that achieved this sort of flow. That was an example of what we called Goldberg-Mohn balance. I don't even know how to spell it. It doesn't really matter. We just use that word. That this particular textbook doesn't use that term, but that's okay. It was just a force balance that required the pressure gradient force, the Coriolis force, the force of friction. If we were away from the surface and we didn't need to worry about the force of friction, then the rotation around our cyclone was geostrophic. I'm just throwing review words here. Where the winds were blowing not in towards the center of the cyclone, but rather just sort of orbiting around the cyclone. But either way, there was counterclockwise circulation, and there was... Oh, what's going on here? We have a couple people missing today for very legitimate reasons, and so we are videoing this lecture. Okay. Remembering, too, that these ideas of these cyclones are pretty big. I mean, a cyclone covers an area like the size of several states. So this is not, something, this is not the center of a tornado or something like that. This is something, a big weather feature, a macro scale weather feature to talk about in terms that we used before the break, etc. All right, so we want to talk about this cyclone. And notice that we append this vocabulary, this adjective here, mid-latitude. We talk about it as a mid-latitude cyclone because it's a cyclone that happens in our part of the world. It's going to be associated with fronts and jet streams and so on. There are other kinds of cyclones out there. For example, a better word than hurricane is tropical cyclone. Okay, so we have hurricanes and we have, which are tropical cyclones. We will learn about them in the next unit. For now, though, we're going to be focusing on mid-latitude cyclones, the kind of garden variety, low-pressure systems that pass through every few days. All right, so let's talk about the life cycle of a mid-latitude cyclone. And in order to have a life cycle, we need to start off someplace. We're going to start off with the idea that someplace in the country at some time there's going to be a stationary front. We're going to have some kind of, these are all things that were scanned and are available to you on Blue Line. If you haven't printed them yet, I would encourage you to do so. So we're going to have a stationary front. Now remember the stationary front, again just to throw more vocabulary words at you, remember the stationary front was an example of the polar front. And the polar front should be found pretty much, we should be able to find it someplace around the world, all the way around the world. It's separating that cold air from the north from the warm air from the south. So let's go ahead, we're going to work on the assumption that if we looked around for a while, we'd eventually find a stationary front. Now, that stationary front will sooner or later develop an area of low pressure along. So right now I'm putting a little area of low pressure along that stationary front. Notice that the stationary front has cold air, in this case I labeled it CP, maybe this is continental polar air, and to its north, and it's got some warm air to its south. In this case I labeled it MT for maritime tropical. Both of those are air masses, so by definition they're higher pressure. So the air masses on either side of the front are higher pressure than what's on the front. But why we actually made an area specifically of low pressure on the front and made it spin in a counterclockwise way is an example of what, I'm just going to put a powerful vocabulary word here, this is going to be the second half of our lecture. This is going to be an example of what we call cyclogenesis. Cyclos, like cyclone, genesis, birth of. We haven't yet in this course explained why cyclones happen. What actually causes areas of high and low pressure. That's what we're going to be doing in the second half of today's lecture. But for now, let's take it as an article of faith that it will happen, okay? We need to explain the life cycle of a cyclone before we can explain how they get started. So, take it as an article of faith for right now that given some time, an area of low pressure will form along that stationary front. In the second half of the lecture, we'll explain why. So we've got this area of low pressure, and because of the things that we learned in the second unit of the course, like the forces that will be existing around that area of low pressure, we now know that the winds will start to rotate in a counterclockwise way. But as the winds start to rotate, notice what they're doing. They are moving air masses. That stationary front, which was the boundary between a cold air mass and a warm air mass, isn't going to be so stationary anymore. At this stage in the life of the cyclone, those fronts start moving. And we start getting something that looks a little more like this. I mean, we learned on our lecture about fronts, which I think was the last lecture before spring break, that cold fronts and warm fronts and stationary fronts are kind of all the same thing. I mean, a cold front is just a stationary front that's moving with the cold air pushing the warm air out of the way. A warm front is just a stationary front where the warm air is pushing the cold air out of the way. Now we can see why those air masses were moving, which was a great question we had that day, was why were the air masses moving so that we had fronts. Now we see why they're moving. They're moving because there's a cyclone, and the cyclone has this large-scale counterclockwise rotation that is pulling on its west side, pulling cold air from the north down towards the south. And up on its east side, it has warm air being pulled to the north. That's why the air masses are moving. The cyclone's doing the work.